Hi, Scott. This is the section on transmission lines, and I know you had some questions about that, and we'll be able to take a look at that this in this little video. This is a tool that I use. This has been so helpful to me. This is a program called SimSmith. It's by a guy named Ward Harriman. KA8SMA. This is a free program. It's amazing. I've learned more about transmission lines and matching circuits from this in the past year than in the previous 50 plus years that I've been a ham. It's been very helpful. Hopefully you'll get to see a little bit of that. It has it's a user interface that is a little bit unconventional. But after you get used to it, it's really not that hard. And after you get used to it, you also see why Ward Harriman made the choices he made, and it actually makes it very easy to use. Hopefully you'll be able to see a little bit of that as I talk about your specific antenna. So we had talked in the other video about how EasyNet generated the complex impedance model at the feed point of your loop antenna. I've taken those values and I've imported them. Here into SimSmith, and you might recall even that we talked about the impedance at 14.1 megahertz. We said it was pretty close to 240 ohms resistive and minus 575 capacitive, and that's exactly what we see here at this frequency. In fact, if I change this frequency, you can see these values up here change as I change frequency, and that's exactly what we want. So internally here, this file has a table of all those impedances for the 20 meter ham band. Over here we have a Smith chart. I have it set right now. I have this impedance set to 450, mainly just to make this a little easier to see. And so on a Smith chart 450, when this is set this way, 450 would be at the center. And we'll call this the target impedance, or the impedance of the transmitter. It's labeled G here for generator, which apparently is a convention with this kind of thing. Just a quick review of the Smith chart. The center will be the reference impedance, and we see it on here in faint lettering. It's 450. Everything along this line, this horizontal line, is resistive. So if you go all the way over to the left, this would be 0 ohms. This resistive, this is our characteristic impedance of 450. And then if we go all the way over to the right, this is open circuit or infinite ohms. So you can see it's also a nonlinear scale. And then in this plane, everything above the line represents a inductive reactance. Everything below the line represents a capacitive reactance, and so if there's a spot that's away from this line, it will have some component of resistance and some component of reactance. And if it's above the line, it'll be inductive reactance. If it's below, it will be capacitive reactance. So with this impedance set to 450, we can see this line over here. If I click on that dot, that's where we're at right now. It represents the 14.1 megahertz. In fact, you can see if I scroll this around, we'll go to 1400. There's the beginning, and then if I scroll the frequency along, there's 4.2, there's 4.25, 4.3. and 4.35. And that really just maps the numerical values that we have up here in the corner for the resistive component and the reactive component. In fact, if I click a cursor on here, down here we see we see an impedance of 171. That matches our 171 up here. And the reactive impedance is minus 308, and that matches our minus 308. So get this. Oops. Get that out of the way. My point in saying that is that this line that we see on here just maps the numerical values. Now I'll run this back to 14.1 megahertz, and I'm going to change the impedance to 50 ohms because that's what our transmitter is. This is the same group of values, but they're moved to a different area of the Smith chart now because 50 ohms is at the center, and these other values that we saw are way over here. And because it's a nonlinear scale, the further you get away from the center, that line that we used to have down here has now sort of been compressed into this shape, and it's over here. Okay, let's see what happens when we add a transmission line. And you had questions about 450 ohm ladder line, 300 ohm ribbon line, and 600 ohm open wire line, or we'll just say at 600. Obviously, you can change that with various spacings. So let's drag a transmission line up here. And for right now, I'm going to make this transmission line very short. I'm going to make it 0.1 feet long. And so let's see here. Down below, I'll turn this on. See this pink color up here? That's the impedance at the feed point. And then this blue color here is the impedance as it appears at the generator or at the transmitter. And that's, I've enabled it down here at the bottom. Because the transmission line is so short, it says 0.01 feet, these two values are almost identical, and that makes sense. I mean, you can see it here. It's transformed it just a little bit. Even, it's kind of interesting, isn't it? It's transformed it a little bit, even with that shorter cable. Let's talk about the cable itself for a minute. This has defaulted to 50 ohm coax. That's not what you're using. Let's pick the transmission line that you're actually using. This program comes with a list of popular transmission lines. There's a lot of them in here. For you, we'll start with the 450 ohm type. And interestingly, most of the commercial 450 ohm ladder lines are not 450 ohms. They're less than that. I'm going to pick a Wireman 553. This is a type I've used before, and we see that it's actually 395 ohms, but we'll pick that, and that has loaded it in here. We see a velocity factor. These are measured values, by the way. This is from this table. It's a velocity factor of 0.90. Characteristic impedance of 395, and then these three constants here represent the DC resistance loss from just the DC resistance, per foot, the loss from skin effect at whatever frequency is being operated at, and then also the loss from the dielectric material. So the polypropylene dielectric material, the webbing, well, I guess with ladder line, it's a section of polypropylene webbing, and then air, and then polypropylene webbing, and then air, and the net effect of the dielectric loss from that polypropylene is reflected in this set of coefficients, and I don't remember which one it is. I think it's I don't remember which one it is. I think it might be K2. Anyway, it's a pretty comprehensive model of the transmission line. And if we look up here with our very short transmission line of 0.01 feet, we see that we know that ladder line has a very, very low loss, relatively low loss, which we'll see here in a minute. But we can see that that's hardly changed the impedance. It's hardly transformed it. We went from 240 ohms resistor to 239, and from minus 575 to minus 574. But let's see what happens when we start adding length to it. So I'm going to just change this to 1 foot. And now we see that these don't line up over here. They're not quite on top of each other. And I'll just start using my scroll wheel on my mouse to just start adding some footage to this. So now we're up to, well, let's see, now we're up to about 10 feet. And look at how dramatically these impedances have been transformed just by the transmission line. In fact, this is an impractical length to operate from with this antenna, but look what's happened here. The transmission, these complex impedances, now this is at 14.1 megahertz, that has been transformed. We now see it's laying right on that horizontal line, which means that reactance is near 0. And if we look over here, we see that it's landed a little bit above 50 ohms. It's 73 ohms. That's an SWR of only 1.47. We've taken this, these wild values with a horrible mismatch to 50 ohms, and just with the transmission line, we've transformed these impedances to something that is close to useful at this point. Now our target is 70 feet. Just for the sake of understanding this better, let's just keep adding some length to it. And you can see it just goes around in this big circle. This is the classic, this is the behavior of transmission line. This is what you see. It just rotates round and round, and it's centered on the characteristic impedance of the transmission line, which on the graph is somewhere over here. Again, it's nonlinear, so the center is offset a little bit. But it just keeps rotating around this. In fact, if we come in again, come in closer, whoops, let's see here, if I can, have to increase the number of digits here. Let's see, there we go. So I can really zoom in on that spot. Here again, we've come near resonance. Now this is getting to be a little more realistic distance. So without any matching tuner on this, we've transformed this just with 41 and a half feet of transmission line to 77 ohms. We also see this other effect here where this is sort of spiraling inward. It's not lined up exactly on top of the first time around. That's due to the losses in the transmission line. So although they're quite low, there's still a finite. There are losses. In fact, if you take another little excursion here, if I were to just start cranking this up and adding transmission line, now we're up to almost 500 feet of transmission line. You can see the losses accumulating. This is the behavior of any kind of transmission line. It doesn't matter whether it's coax or ladder line or open wire line. It would take a lot longer to get here, but it would do it. The further you go, the more it begins to converge on its characteristic impedance. And if you get, we're at 2,500 feet of transmission line here. If you go far enough, eventually it will just look like a perfect match to its own characteristic impedance, and the rest is just lost. There's hardly anything getting the antenna. So that's just a little side trip there. Let's just change this. Let's just change this now to the target that we want to hit, 70 feet. That was the number you gave me. So with 70 feet on 20 meters, and this would be different for the other bands. Of course, they would have their own set of complex impedances, and so it would start from a different place and rotate around that. This is just for 20 meters, but we see that over here on the Smith chart, we see the sweep that we had here, this pink line, via the transmission line has been transformed now to this place. In fact, I think I can turn off the visualizing the transmission line, and now we see we're at this new place. So this is kind of interesting here. I guess I could run this up to see where it's resonant. It's resonant. It's 100 ohms, 2-to-1 SWR, without a matching network at 14.28 megahertz. Let's go back to our 14.1. Now, either with a built-in match in your rig or an external match. I'm going to guess that with this antenna you have an external match box, a tuner. This SWR here of 5-to-1 is a bit high for an internal one. We could add our own, make an L network here, but I'm just going to use this, I'm just going to drag this auto match up here. Let's turn our sweep back on. So what's happened? The colors have changed on us, but this was our original values, the original sweep at the antenna feed point. The dashed lines are the transformation due to the 70 feet of transmission line. We ended up here for the 4.1, and now this capacitor, this shunt capacitor, has moved this point to here in the Smith chart, and then the series inductor has gone from this point and rotated it right up to 50 ohms. So these are values that probably somewhat close to whatever you're using on this band at this frequency. And we've got a perfect 1-to-1 match. So let's just take a look over here. We're going to look at, we're going to leave the Smith chart, and now we're going to look at this. We're going to look at it in terms of SWR. So, so this is looking pretty good. Here's SWR of 2. Of course, with your tuner, you could tune this to anything. You could move this around. In fact, if I move this to 14.25, just to show you that it can be done. Well, now we're way up here. We've got an SWR of 2.6-to-1. But if I tell the auto tuner in here to match that frequency, boom, we've got this fantastic match at 14.25. So let's see here. I know you want to talk about some other transmission line. Let's move this back to 14.1. It's just to be our reference. We'll get this back to 14.1. And we're going to take a look at some different types of transmission line now. One of the things about ladder line is that it can get wet, it can get snow on it, it can get ice, and that changes the dielectric, and it also changes the loss in the dielectric. Fortunately, this has been modeled for us. So Wireman, we were using Wireman 553. They also have here in the list Wireman 553 ice and snow. So it's lowered the characteristic impedance, but it's also changed. Well, I'm going to back up a step. Sorry, there's a thing I skipped that I want I want to do. So we're going to go back to where we were. I want to look at the power that's reaching the antenna. So I need to change this real quick. Just add this. And then I'm going to add 100 watts. I know you operate QRP, but it's just, you'll see in a minute, it's a little easier to see some of the proportions. It's easier for me to grasp in my head what the losses are. So if we look up here, we see that with this this coil, I'm certain most of the losses in the coil. With a coil, it has a Q of 200, which is a reasonable value. If it had a higher Q, the losses would be lower. We've got about a watt of loss. So you start with 100, and we lose about a watt in this L network tuner. But then look, we're losing almost 13 watts in the transmission line, and then 86.2 watts are making it to the antenna. So I remember when I first started playing with this was a bit of an eye-opener, because I had always thought that ladder line, especially ladder line, would have virtually no loss at high SWR. And it's way better than coax, that's for sure, but it is a finite amount. And the reason is that we've got, we have this coax with a characteristic impedance of 395 ohms, but that is not the impedance at this end. It's dramatically different from that. And so we have these these losses due to mismatch in here. And with the losses due to the dielectric in this, the dielectric losses in the material, the mismatch in impedance just exaggerate that. So if this happened to be a way better match to 395 ohms, this value would be a lot smaller. And you'll see that on some of the graphs for the other bands, where by coincidence it just happens to be a better match. So I want to take the next step then and look at what happens when the ladder line has snow and ice on it. So we'll go back and select that, as I started to do. So here's the 553 with snow and ice on it. So the velocity factor has changed a little bit, the characteristic impedances have changed a little bit, and these coefficients have changed quite a bit. And now we see we've got about a half a watt loss in the L network, the matching network. But look at the big loss. Starting with 100 watts, we're losing 38 watts just in the transmission line, and it's because of the snow and ice that are on that ladder line, and we only end up with 61 watts or so. Of course, if I change this wattage here to 5 watts, you're losing almost 2 watts in the transmission line, and with only about 3 watts getting to the antenna. But let's look at this yet another way. Let's look at it in terms of decibels. Okay. So let's see here. Let's look at it in terms of power. dB watts. Change the scale over here. Move this around. All right. So we've seen, dBm, that's dB milliwatts. This is dB watts. So 20 dB watts is the same as that's equivalent of 100 watts. It's 10 to the second power. The formula, you multiply the exponent 2 by 10, that gives you your 20. So 20 dB watts is the same as 100 watts. So what we want to see is how close this comes to 20. And the the extent that it is, whatever the difference is between this and 20 is what our loss is in terms of dB. So this is about 2.1 dB lower than what we would have if all the power made it to the antenna. The threshold of perception is around a dB, so 2 dB is a third of an S unit. You know, it's not, even with that 40% loss in the transmission line, it's still not the end of the world. And I don't know whether you've noticed, you might not have noticed it at all. I mean, 2 dB is, you have to really be paying attention to notice the difference between, you know, to notice a 2 dB loss. I suppose if something's really down in the mud below the noise level, 1 or 2 dB might make the difference between, you know, copying it and not. But it's there are probably bigger problems with noise and fading that are at least as big as 1 or 2 dB. So let's switch this back, and we can take a look at the power in terms of dB with the dry ladder line. So now we see it's 19.4. So our loss dry really only represents 0.6 of a dB, and that's very likely to be below the threshold of what you could even perceive. So let's take this back to watts, which I just did. Now, you are also interested in 300 ohm transmission line. I did not include that in any of the graphs that I sent you. All of it was done with this Wireman 553 dry 70 feet, and now you know what all these values are. Let's change this around a little bit so it matches something close to what you're seeing in the graphs I sent you. So this is SWR, which we looked at before. That's on this scale, and this lighter blue line is the power that's making it to the antenna. So now I think you've got the very detailed picture of what's going on in all those graphs that I sent you that look like this. So let's take a look at the 300 ohm transmission line. They do have a sort of generic 300 ohm. This is 300 ohm tubular. That's not the same as ribbon line, but just for the sake of exploring this a little bit, I don't have the measured differences between this stuff and ribbon line. It sounded like you were using ribbon line, but I don't really know. But I think you'll get the gist of it. You'll get the idea of it. We'll go back here for a second. It has ended up in a different place, and I can see if we start with I'm over here in the Smith chart, if we start with our sweep, our original sweep, and then we've got 70 feet of the ribbon line, it's going to rotate around its characteristic impedance of 300 ohms. It's going to end up, well, let's see, it's going to end up here this time. It's different transmission line. So before we ended up down here someplace, now we end up here, and the matching network does the rest of the transformation. So the capacitor, the shunt capacitor brings it down here following the green line, and then the series inductor brings it up here to 50 ohms. This is what the impedance looks like at the end of the 300 ohm, taking these values from the feed point impedance, and then the transmission line transforms them to these values. The L network tuner transforms it the rest of the way we need to go to get to 50 ohms. So let's look at the power losses. Start with 100 watts. We lose 1.5 watts, mostly again in the coil, I'm sure, with a Q of 200. And then we lose a little bit more power than the ladder line. We lose 17 watts for at 20 meters anyway. We lose 17 watts in the transmission line and end up with 80 watts. Really, between this and the 450 ohm ladder line, I doubt you'd hear any difference. These differences are really not going to be perceptible. I don't remember what they are. I did take a peek at what they would be on the other bands, but in most instances they were more comparable than not. So a little bit more loss with this 300 ohm line. Maybe if you had 300 ohm line that had windows in it, it might be a little bit less. Actually, it might be more comparable to the ladder line. You'd really have to evaluate it on a band-by-band basis. But last but not least here, let's take a look at what happens with this with the 600 ohm open wire line. So that's on here. So that's here, just generic 600 ohm open wire line. And a couple of things that we can see. Here again, I'm looking at the Smith chart. Here again on the right, we see our original sweep. But look how tight this is. That's the same length. It's gone around several times. You can see that as it has spiraled in, there's not much loss. It kind of stays right on top of itself. We end up here. That's the end, and then the L network transforms it the rest of the way to 50 ohms. We'll go back to this graph. Let's look at our losses out to the antenna now. We start with 100 watts. We lose about a watt in the inductor of the L network, but look, only 3 watts of loss in the ladder, or the open wire line. I mean, it's almost nothing. And so most of it's getting to the antenna with this, and I can tell you from having looked at this on all the bands with your antenna that it's like that on all the bands. Let's look at it in terms of dB. 0.2 of a dB loss from rig to antenna. Is this enough to make a difference? Well, is this enough to warrant switching from the 450 ohm ladder line to this? It's hard to say. If you're a member of the Last DB Club, then the answer is yes. But you also know that the open wire line is, it's more of a hassle to mess with, and doesn't have the convenience of the ladder line. So under dry conditions, might not really be worth it. Under wet conditions, snowy or icy conditions, it definitely would be a consideration. So anyway, that's it's more than an overview. I've really given you the detailed tour of what's happening with the transmission line on your system, using 20 meters as an example here. And I hope this makes seeing the other graphs more meaningful, and I hope it's been helpful. If you have any questions, let me know. Thanks.